it looks like this. Bloop. Try it.
Yeah. Yeah.
Because they're opposite charges. Okay, keep moving. Now, the ion moves to which, a little slower, thank you. Which rod does the ion move towards? The negative. So, whoo, whoo. Now see how I'm actually moving ions now physically. So a dipolar moves the ions.
So does it basically scan out across all possible frequencies too?
No, it never changes frequency.
It's the same frequency.
It's always the same frequency, and what we do is we use the quadrupolar to move ions up to its frequency. So the red asterisk never moves. The red asterisk remains the same, as it never changes frequency.
So you scan across the...
What? Right, we use the quadrupolar to change an ion's frequency to match the frequency of the X rods. When it matches, the minute it matches, it comes in resonance. It experiences constructive interference, starts moving out. This motion goes out, and it ejects them. The dipolar physically increases the X motion so large that it goes out the slits, and what's outside the slits? The detectors. Okay.
So you scan through the quad RF amplitudes until it reaches this resonance.
Right, you got it. So we take the quadrupolar, the center section RF, and we ramp it. Notice its frequency is always the same. We ramp the amplitude. Okay. This causes ions to start walking across the line. Okay. When they hit the asterisk, they're kicked out. Okay.
So does that use different rods than the quadrupolar? So there's a total of 8 rods. So is it
There's 12 actual rods. There's center, front, and back. The center, the back, and the front don't count at all because those are purely for Z motion. It's the 4 rods in the center that we care about. Okay? And those 4 rods have 2 RFs. The top rods have quadrupolar only. The side rods have quadrupolar plus dipolar.
So 2 RFs
on the same rods. Yes. Now, if you want to understand that electrically, you look up the paper of Senko and Schwartz, and they show you the trifilar coil split in half and how you do that. If you want to understand it chemically, like I do, you think every day, what do you turn on in the morning on your car? And you listen to the
motor turning on that.
music. Where do you hear music? You turn on your FM radio. Okay, if you think about FM, FM is the guy's voice frequency sitting on top of the FM carrier frequency. Because you turn on a frequency of 98 megahertz, that's the first RF, and then you hear the guy's voice superimposed over the top.
So it's RF on top of it.
Yep.
So it's a bumpy curve.
Yes, exactly. Okay.
Who came up with that?
The RF on top of RF? Yeah. That was Marconi back in 1870s. Okay. The interesting thing is, if you open up our computers and you look inside, what you're going to see is a Yamaha DX7 synthesizer. It's the exact same chip, the exact same circuitry that appears in a keyboard. Okay? Because we're doing the same thing. We're creating shaped waveforms at specific frequencies. So if instead of hooking these up to rods, if you hook them up to a speaker, you'll hear a boom, 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 boom. Okay, we're making music. It's just a little ugly music. Ions love it. Now, read right here. For linear ion traps, staying away from the stability edge of 0.908. That's why we use this. We don't want to get near 0.908. Minimize the excitation in the Y direction. Remember, I keep saying we don't want to do anything in the Y. By staying away from that, we get no Y direction. So ions can be ejected efficiently through the slot and reduces the scattering effects. Okay? So what voltage ejects the ions? Which physically moves the ions out of the trap?
The quad RF.
The dipolar RF. Applied to what rods?
The X.
To the X rods. What voltage changes the frequency of the ions to bring them in resonance with the dipolar? The quadrupolar RF. So the quadrupolar RF changes the frequencies. When the ion's frequency matches that of the X-rod dipolar, it comes in resonance and it gets kicked out. Okay, does that make sense? Cool. You're now in the upper 5% of ion trap users who can actually explain somewhat intelligently how their trap works.
So what does that look like? So we have a wave over a wave. What is this?
You mean the dipolar on top of the quadrupolar?
Yeah, what is that? Is it like if you drew that, what would it?
Oh, I can draw it for you exactly what it looks like. What you end up seeing is... Okay, hold on. I mean, if I was a decent artist. All these should be...
So the little squiggles are the
dipolar. Because the little squiggles are about 1 to 15 volts peak to peak RF. The big guy is anywhere from 200 to about 15,000 volts peak to peak RF. So it's a little tiny sine wave on top of the bigger sine wave that's in, okay?
So what causes the resonance ejection?
It's this little wave. Okay.
So it just matches the frequency of oscillation of the ions?
Right. Right. Dipolars only work when the frequency of the ion matches the frequency of the applied voltage. Quadrupolar works no matter what frequency. Okay, as long as the amplitude's controllable. Okay. Me and my brother would like to think that there must have been other children in our family our parents never told us about who inherited all our artistic ability. Okay, does that make sense? Questions, thoughts, or comments? Any questions, thoughts, or comments at all? You completely understand how the ions come out of the trap.
What makes the big curve get bigger as you go along?
That's when we're changing the amplitude of the quadrupolar.
That's when you're scanning.
And that's when the ions are moving up to the ejection point. So the change in the big guy's amplitude is what changes the frequency. Okay. So you might have something like...
Does that also change the kinetic energy of the ions, or just...
No.
So kinetic energy is a constant.
Kinetic energy is a constant of the quadrupolar. Okay. The dipolar affects the kinetic energy of the ions.
Okay. So obviously when it resonance ejects, it gains.
Then the kinetic energy gains. Okay. Quadrupolar does not affect kinetic energy. Okay. Cool. Okay. You can ask me questions during the week if you want to kind of think about it and come back to it. Okay. And this shows you a picture. You're looking from the FT's point of view. So it's like you're standing inside the FT and looking down, and the slots are going into the board right here. So the ions are going.
So they're inside that little circle in the middle? Is that
yep. Oh no, that little circle, that's the hole to the FT. That's probably a good 1/4 inch, I think.
The end caps.
Right.
What do you call these end caps?
End sections. Okay, and this is just a little conductance limit to keep the helium inside. Okay, so on the ends of the end sections, which is what really keeps the ions contained, there's 2 little plates. Okay, that just match the DC RF of what the end sections are, and they're only there so that way we can fill the helium, and the helium doesn't just
so the helium
spew
coming in through the helium at the top.
The helium's coming right here.
And what's that other tier up there?
This guy?
Up higher. The white tier up.
Oh, that might be the helium. Oh, maybe I'm not looking. No, these are just wires. I thought that was plastic. There's your helium right there. You only have one helium link.
So I could set down into that.
Yeah. You have 2 conversion diodes. They convert positive to positive. They convert negative ions. What they do is they make a small molecule and a peptide give you the same signal response. They just blow the ion up into little pieces. all the little pieces are blowing down the electron multipliers to actually create your signal. Okay?
So as you amp up the RF amplitude on the quadrupoles, as they eject, they match the resonant energy, they get ejected, they get blown apart in these detectors, is what you're
Yep, the ions come out, they suck up